Hello, chemists. This is Ms. Placino, and you're watching lesson 13.7 on balancing redox reactions. In today's lesson, we're going to look at some more involved problems that require balancing redox reactions. Specifically, our one goal for the lesson is to use the ion-electron method, basically just a very specific technique to balance redox reactions that are occurring in acidic solutions. This is definitely more of an advanced topic, but I know you can do it. Let's go ahead and get started. All right, so the technique that we're going to be using is called the ion-electron method of balancing, and hopefully the reason for that name will become apparent as we get going. So as it turns out, many redox reactions take place in acidic environments. And based on what we've talked about with acids in the previous unit, what do you know has to be present if you've got an acidic solution? Hopefully you're thinking H+ ions. We know areneous acids release H+ ions into solution. So that's the ion that we're going to use to balance. In addition to H+ ions, since all acids, at least the ones we're going to work with, have to be aqueous, we know that there will also be water molecules present. So in this technique, we're going to use hydrogen ions and water molecules to balance our redox equations. And just as a reminder, all chemical equations, regardless of what type they are, have to be balanced for mass, charge, and energy. So the two that we're really going to be focusing on today are mass and charge. And I think for this lesson, it makes more sense for me to go through the notes instead of going through a PowerPoint. So this is the reaction that we're going to be focusing on. We've got a dichromate reacting with nitrite to produce chromium and nitrate. And in the technique that we're using, we know that we've got H+ and H2Os to help us balance. So our first order of business is not too different from what we do when faced with other potential redox reactions. We're going to assign oxidation numbers, or oxidation states, remember, one and the same, to all the elements in the equation. So let's take a look. I've got chromium and oxygen. Oxygen in almost all situations is a -2, so 2 times 7 gives me -14. And I have a -2 overall, so I need a positive 12. 12 divided by 2 gives me +6 for chromium. Oxygen, -2 again. This is a -1 ion, so this must be a +3 from nitrogen. Chromium 3+, that's a freebie. It's got a a charge of +3. Oxygen, -2 again, so that's -6 in total, charge of -1. So nitrogen must have a +5 oxidation state on the product side. How do we know this is a redox reaction? Well, the same way we know all other redox reactions are redox reactions. We've got changes in oxidation states as elements move from reactant side to product side. So we're going to identify which elements are involved in the redox reaction by looking for changes in oxidation number. All right, so chromium and nitrogen are two elements that are involved in the redox reaction. Oxygen really is kind of a spectator in this case. Its oxidation number does not change. It's a -2 everywhere you see it in the equation. So we're going to write the half reactions. So let's look at the chromium part first. We've got chromium in dichromate as a reactant turning into Cr3+. So I've got Cr2O7 with a charge of 2- and Cr3+ on the product side. So the first thing we want to do is balance all elements that are not hydrogen or oxygen first. So really what that means for us in this particular example is to balance the chromiums. We've got 2 chromiums on the reactant side. If I put a coefficient of 2 in front of Cr2+, I now have 2 chromiums on the product side. We're going to balance our oxygen atoms using water. This is an acidic medium. We're told that this reaction takes place in acid, so we know there's going to be water molecules present. I have 7 oxygens on the reactant side. So on the product side, I'm going to put 7 water molecules. That'll give me 7 oxygen. So I balanced the oxygen, but I've created a new problem. Now I have hydrogens. I'm going to balance the hydrogen atoms with H plus ions. So I have a total of 2 times 7, 14 hydrogens. Ooh, that's a lot. So I'm going to include 14 hydrogen atoms. This is an acidic medium, so I know there'll be hydrogen ions aplenty on the reactant side. Okay. Finally, we need to balance for charge. And we're going to do that with electrons. Hence calling this the ion-electron method of balancing. All right, so let's look at the total charge on the reactant side. I've got positive 14 minus 2. So I'm just going to jot down like a plus 12 over here. On the product side, I have 2 times positive 3. So that is a plus 6 on the product side. Okay, I've got electrons to balance charge. Looks like I need 6 electrons on the reactant side to balance up the charge. So we've got a total of plus 6 on both sides. Let's do the same thing for nitrogen. Nitrogen is an NO2 as a reactant, and NO2 minus and NO3 minus as a reactant and product respectively. We're going to start by balancing all elements that are not hydrogen or oxygen. So in this case, nitrogen. There's 1 nitrogen on both sides of the equation. Up next, we're going to balance oxygen with H2O. So I've got 2 oxygen on the reactant side, 3 on the products. If I put an H2O on the reactant side, that'll give me 3 oxygens on both sides of the equation. I fixed the imbalance of oxygens, but now I've created an imbalance with hydrogens. I'm going to balance up the hydrogen atoms using H plus ions. I need 2 of them to completely balance hydrogen. Make this a little bit neater and easier to read. Okay, now it's time to look at charge. So I've got minus 1 on the reactant side, and I've got minus 1 plus 2, so that's a plus 1 on the product side. If I add 2 electrons to the product side, that should balance up the charge. Whew. Okay, so that is pretty labor intensive. Now you really want to work through these types of problems stepwise. Now that we've got our 2 half reactions, we want to combine them together. So combine the half reactions. Just like some of the other redox reactions we've looked at, we want to make sure before we combine that the electrons lost in the oxidation reaction equal the electrons gained in the reduction reaction. So I've got 6 electrons in my reduction half reaction. I've got 2 in the oxidation half reaction, so I'm not ready to combine these just yet. I can get this balanced by multiplying to get the correct coefficients. So let's go ahead and do that. Okay, I need 6 electrons, so I think I need to multiply everything by 3. So that would give me 3 H2O, 3 NO2, 3 NO3 minus, 2 times 3 would give me 6 H plus, and 2 times 3 would give me 6 electrons. Okay, so we're going to combine these 2 half reactions. We can do a lot of simplification and kind of get things to cancel out. So substances that are on the products and the reactant side can be canceled, or at least simplified. All right, so let's give this a shot. Let's add them up. So the first thing we should do is get rid of our electrons. 6 on the products and 6 on the reactant side, those cancel. If we take a look, we can also kind of simplify water. I've got 3 on the reactant side. I have 7 on the product side. So that's kind of a net of 4 over on the products. I can do the same thing with the hydrogen ions. I've got 6 on the product side. I've got 14 on the reactant side. So that's going to wipe out all the hydrogen ions on the product side and give me a total of 8 H pluses on the reactants. I think that's all the simplification we can do. So combine them. On the reactant side, I have 8 H plus. Now let's be consistent. I have Cr2O7, 2 minus, the dichromate ion, and I have 3 NO2 minus. So those are the reactants. Not going away. Oh, there we go. Sorry about that. On my product side, I've got 2 chromium 3 plus ions. I've got 3 NO3 minus ions, and I've got 4 H2Os. Now I am, or at least I should be, balanced for both mass and charge. I know this was a lot of work, and kind of the tendency is just to like take a deep breath, relax, put your pencil down and admire your work. But you really should take just a little bit of time to check your work. Make sure that this equation is balanced for both mass, so the same number of atoms of each element on both sides of the equation, and charge. All right, let's just quickly do that and make sure we've got it. 8 hydrogens. I've got 4 times 2, 8 hydrogens. Those are checked out. 2 chromiums, 2 chromiums. 7 oxygens plus 2 times 3, give me 6. So 13 oxygens. 4 times 1 is 4. 3 times 3 is 9. 9 plus 4 is 13. So far, so good. 3 nitrogens and 3 nitrogens. I am balanced for mass. Let's look at charge. Positive 8 minus 2, so that's a positive 6. Plus 3 times minus 1, so 6 minus 3, that gives me positive 3. Cr3 plus, I've got 2 of those, so plus 6, plus 3 minus, that also gives me plus 3. So as far as I can tell, we are balanced for mass and for charge. This is finished. Again, I know it's a lot of work, so just to quickly review the steps. First thing we want to do is assign oxidation numbers, just like we do for any other redox reaction. You should have 2 elements undergoing changes in oxidation numbers. You'll write out your half reactions, write the entire, like in this case, ion, that the element undergoing oxidation or reduction is present in. Once you've got that figured out, you want to balance all elements that are not hydrogen or oxygen first. Once that is squared away, you're probably going to have some oxygen atoms you need to contend with. Balance oxygen with H2O. As you balance the oxygen with water, you are now going to create an imbalance of hydrogens. So on the opposite side of the equation, add hydrogen ions, since this is taking place in an acidic solution. Finally, take a look at charge. Balance charge using electrons. Once electrons lost in oxidation equal electrons gained in reduction, you can combine the 2 half reactions, completely canceling out the electrons, and then simplifying down water and hydrogen ions. You probably will not be able to simplify anything else. Add them together, check your work, and that's how these get solved. So again, it is involved, it is challenging, but I know you can do this. All right, chemists, thanks for tuning in. I hope you found this helpful.